All right, can you guys hear me online okay? All right. Is there any confirmation online that you guys can hear me okay? Hopefully you can hear me. Good, thank you for that. All right, we just have an announcement today. All right, good morning. We have an announcement, so I'll let you guys go ahead and make your announcement.
Hi guys, I'm Kaylin. I'm from the Society of Women Engineers, and I just wanted to tell you guys about our biggest professional development event that's coming up called Evening with Industry, or EWI. That is where we have all of our company sponsors. All of our sponsors are engineering companies. Last year we had some really big names like Boeing, Somas, Goldman Sachs. Yeah. This year we have over 16 company sponsors, I believe. And at this event, you dress up business professional, sorry. We're a business professional and we have a networking hour with these companies. And then you get to have a sit down dinner at a specific company table. And then you rotate for dessert. And it's just a really great opportunity to connect with these companies and their representatives and actually ask them what they want in industry, or like ask them what they're looking for internships or for full-time jobs eventually. Yeah.
You can like get jobs, like we know people that have gotten jobs out of this event.
Yeah.
Like a friend of ours just got a full-time offer, so.
Yeah, so it's a really great chance to connect with these companies. It is on
September 26th from 6 to 8:30. Your professor should have a flyer. Did you see that?
I don't know if it was on that email. Just send me another one and I'll post that.
There's also flyers outside.
Yeah, they're on like every single table, and there's a QR code where you can sign up for more information.
Yeah, so it is $10 in advance, $15 at the door, and that'll be at the Alumni House, which is where you pick up your bus tickets. Yeah, does anyone have any questions? Perfect, thank you so much.
Okay. Thanks. Okay, so a good opportunity to network and get some connections. Let me, no, this is not. All right, so last time, I guess actually another announcement. My apologies, I did not realize that that RLC quiz was not on the modules page, so I've extended that deadline if several of you missed it. If you've already taken the quiz, great. If not, I extended the deadline till this evening, so please make sure you do take that quiz so that will give you practice to see, you know, where am I in my knowledge? So it's a great assessment to figure out where you are. All right, questions about the assessments or that quiz? Any other questions? Okay, so exam next Wednesday. So September, I think it's the 21st. Yeah, 21st. So next Wednesday, and it will be same time frame that we have in here. So 8:05, 8 o'clock even, a little bit before 8 if you want to come a little early. You can get started right away and have a few extra minutes. And it will go till 9:30. Again, some of you have class after, so if you have class right after, you'll have exactly 100 minutes for it. So if you want to come a few minutes early, it's timed, and then it will just cut off at 100 minutes. So anywhere in that time frame. Okay, so next Wednesday, Ingman Lab is the name of the lab down there. It's in this building. If you want to just, you can take the stairs down, or you can go from the bottom and up. And it's L210 is the room number. If you use your phone to scan, or if you don't use your phone but want to, make sure to bring that with you so you can scan your work afterwards. There is a scanner in there, but it's a little slow. So I would suggest bringing your own item to scan. Own device, I guess I should say. Again, if you don't have a device to scan, there is one down there. But you will want to scan your work in order to get partial credit. Yes. Yeah, so it will be similar to the quiz. It will be a question, and it will ask you for an answer. And then if you get it right, it will mark it automatically. If not, the grader can go through your partial work to give you credits for the partial. Yes. Yes. So the CADE lab, if you haven't gotten an account, usually by now you do. So if not, you can go down into there and actually do a setup to get your CADE account started. There might be a way online. It's called the CADE lab. So do make sure that you have a login and that you remember what it is, or reset it. It will be multiple questions, but there'll be partial credit given for those questions. So exam content will be 3 to 4 questions. One of them may be like question of another question. So one will be an RC circuit, RL circuit, RLC circuit. We'll go over some of those today. I meant to last time, but didn't get to that yet. So we'll go over some of those concept questions today. So this will be the exam content. Does that clarify your question? Okay. And you had a question?
We love to use our personal devices for test, or we would love to use the
Yeah, you can bring your own computer if you want, or own device, and actually just sit in there and take it on your own computer if you want. Yep, you can take the test on your own computers if you want to bring them. We're just going to take it there, so it's all proctored. So yes, if you have your own computer and want to bring that and use your device on that, that's fine. And probably more familiar to you if you are used to your own computer. So if you want to bring your own device, you're welcome to take it on your own computer. It just does need to be proctored and so located in the England lab. One other thing, if you do, there will be a Zoom, so those that are attending on Zoom, you can take it on Zoom. There will be a verification check afterwards though, so it will be a connection with me, and if you are taking it online. So just note that if you do opt to take that, there will be an extra verification step that you did your own work online. All right, there was another hand, I think.
So everything sensitive.
Yep. So if you even want to like create your own scripts beforehand, have those ready. Welcome to, you can use Python, you can use script coding. I'm fine with those. If you already have MATLAB code that you want to, you still have to understand how to plug in all the numbers. So, it's still a test of verification on that, but I don't necessarily care if you know how to do a multiplication. Hopefully you do by now, but if not, then you can use an online calculator. So online calculators are fine. So if you use a script, do include that in your work. So upload your script if you've used a script to do that, so that, yes, it can be checked that you did do the script right. So if you use anything else on there, screenshots of calculator, if you use an online calculator, I would definitely use all that for verification of your work.
You said it was just like fill in the blank, like how it's far over.
Yeah. Yeah, it will be fill in the blank. So it will be like, please plug in this number for this time frame so that it will give you an answer. What's your comment on that?
I was saying if it was multiple choice, that would have been so many chances.
Yeah, I found that the fill in is a little bit harder. And so it just is like, yeah, do all the work and then put in your answer to verify it.
So what decimal point markers do you want us to do?
Yeah, so typically it will be that 4 decimal point. But as some of you saw, like, even if you just put, if it is really like a whole number and you put that in, it's been checking it correctly. So that 4 decimal point is really just for the computer to try to verify if it's accurate or not, but the grader will go in and look at your work. So if you're still off, but you got marked wrong and it was really close and there was just one little mistake, the grader will note that. Yeah, but do practice for like that fourth decimal place is typically what it will be. All right, other questions? Clear about what will be?
For us showing our work, we need to bring our own paper. We're gonna get on paper.
Yeah, so bring your own scratch paper. So yes, bring your own scratch paper to show your work and then have the device ready to upload your work. So it will show any partial work. Anything you do on the computer, take screenshots of it as you're doing it, just to, again, verify your work, and anything that goes wrong, at least you can get partial credits for it. All right, any other questions, comments? Right, and yeah, it isn't just one question, so hopefully that's clear now. All right, so last time we went over the critic. Let's see, this one was a parallel form and it was underdamped. So we went through that parallel underdamped example. On the learning material, I've posted a type of problem for every type of problem. So parallel, overdamped, underdamped, critically damped, a series, overdamped, underdamped, and critically damped. So hopefully you can get practice on those. I would suggest like looking at the problem, like you can download the notes, look at the problem, try and solve it yourself as practice, and then go through and look at the solution to see what you're doing. You can always pause the video and be like, okay, I know how to do now the next steps, and then compare with the answer that you're getting. So that's a good way to help also that assessment of where am I in this learning process. All right, as I mentioned, I want to do a couple kind of concept questions. Yeah, we can go over this one with that. Okay. Well. one more. So one concept question is, what does alpha and omega naught kind of mean? So any thoughts? What does alpha and omega naught mean?
Those are the roots in the characteristic equation. So like when you use the quadratic formula,
Mhm.
then they tell you what you're, like if you have three options, repeated, complex, and roots.
And characteristics. I was trying to think of a name for that one. And characteristics. What did you call the names of the other one? Complex,
Repeated, and real distinct.
So those are the mathematical terms for that. So yes, they help it determine the roots. So what does that mean to have a root of a system? What is a root of a system?
Is it an answer that makes the system true? So in this case, it's typically when it's like at some initial condition.
Correct. So it is a solution answer to the set of equations. So location wise, it's telling you on a graph, like this is when the system is true. So the form. So all of these solutions have the form e to the minus alpha t. From the exponential, when we looked at the RC and the RL circuits, we knew that we had that value of tau, which was the time constant. So tau is related here to alpha by 1 over alpha. And what again did that time constant mean? Go ahead.
It's like, it's 63%.
Yep. Takes, how long it takes. So it's either the initial or the final value, depending on if it's charging or discharging.
Based on the relationship between alpha and time constant, does that mean, oh wait a minute, no, I was gonna say is that place in the period, that's not right.
So the period is going to be different, and it will be for the underdamped case because then you have an oscillation. These, you remember that it's just the description between the final and the initial, and how does it move between those 2 points for the RLC circuits. So it's not, remember alpha is depending on if you're in series or parallel. I didn't write these out. Probably gonna say them wrong. Oh, no, I did. Yeah, I do have it. So series is R RTH over 2LC. And parallel is 1 over 2 RTHC. So with the RC and the RL, that was the tau is specific to those, just having an R and a C, an R and a C and an R and an L. So now when we're looking at an RLC, this is what it is. But remember that when we solve the equation, X prime, and we have it in this form, alpha is actually A over 2. And so for any other configuration, you can actually determine alpha by solving and developing this part, you know, the second order partial differential equation. So if you wanted to look at a circuit that wasn't just a particular RLC, say it was RLC, LC, another L, you know, that would be another component. But for second order, so these are for second order differential equations. This is another understanding question, but I think Taylor, you had a question before I move on.
Well, I think the alpha for series is just R2L.
Yep, thank you. Yeah, I have it written here and I still wrote it wrong. 2 RTHC. Okay, so notice again here, the RTH over 2L is from the perspective of the C perspective. So capacitor. And the 1 over 2 RTHC is because you're looking at it from the inductor location. And that was because of the way you solved that differential equation variable. So that RTH again is from the perspective of where the inductor location is for the parallel form, and then the RTH in the series is from the location of that capacitor form or capacitor location. All right, so another concept question. So I have a second order partial differential. What does that mean as far as what components need to be in there for a second order? Any thoughts? To which? So it would be 2 elements that are in there. So I need either an L or a C, or I can even have a C and a C, or an L and an L, or a way of manipulating them to get those down to just 2 elements that have a time dependency on them. So for every element that has a time dependency, that means that it's putting it at another order of differentiation. So if I have 5 capacitors in a circuit and they're not able to be combined, I would have a 5th order differential. Does that make sense? So a second order, and the way you can determine if you can use these equations is if you have only 2 elements that are time dependent in there. Okay. All right. Back to, so this is kind of a side note, sorry about that, but back to the time constant. So looking at this, if tau is short, it means that it burns quickly. Or if you want to use like dissipates quickly, that means that your time constant is very quick. So I'm moving very quickly from an initial value to a final value. So there's really no time to oscillate in there. And so if it's moving really quickly, that means that alpha is what? Larger or small? Thank you. So if it's large, then the tau would be quick. And if it's small, then the tau will be long, right? Because 1 over a large number will be a small number. So that means that alpha is large, which means that most likely alpha is going to be greater than that omega naught. And so we would be in an overdamped condition. If it's long, if tau is long, it means that it is taking a really long time, and most likely it's going to oscillate to get to that time frame. So there's oscillation typically and decay. And remember, we did the example, or if not, it's on the videos. I can't remember if I did it in here, but R0, it will oscillate forever. It just is a continuous sinusoid. And so it doesn't decay. So the R is what causes it to decay. So it'd be great if that was ideal, right? R equals 0, but there's what's called always parasitics in a circuit. So even though you don't want your wire to be a resistance, it's actually not exactly 0. It's 0 point something usually. And so that's enough of a resistance in a circuit that even ideally, if you have an L and a C, that wire itself will act as a resistor and cause your circuit to decay and finally end. But it takes a while for it to do that. So one other question that's kind of a concept question. What is WD? Anybody know what that WD is?
That's just when you get a complex root factor out a negative imaginary number.
Okay, and it causes what physically to happen? So as far as the transition characteristics, what is it doing when you have? It's what? I heard somebody saying it. So in this case, omega naught and alpha will be equal to 0. Anybody remember the name of what it is? So it's in a frequency. What does the D stand for? Damping. Dampening. Dampening. Yeah, that's called the dampening frequency. And that is the frequency. So when you're underdamped, that is the frequency that the oscillation is occurring in that transition period. So that's what omega D is. So the damping frequency is, well, what am I oscillating? And so when it's underdamped, that oscillation frequency. So these are some examples of kind of those concept questions. Sorry, go ahead, Taylor.
Yeah, so is the reason that you have a frequency dampening for underdamped circuit that you don't for a critically or overdamped is because of the damping? Is it because the only time damping occurs as a frequency curve is when it's underdamped?
Yep, I was trying to remember where these forms are. Let's see. Like, where did the book go? Oh, there it is. Okay. Three. My heavens. Okay. You said it was which page? Oh, this is what I was looking for. Yep, so here's the forms of the underdamped, critically damped, and overdamped. And so you have the oscillation typically with that underdamped one. And so that frequency that oscillation is occurring is omega D. Does that make sense? Okay. All right, so these are kind of concept questions. Other types of concept questions. So going back to our example yesterday where we had, this was a parallel circuit. So parallel RLC circuit, and it was underdamped. What would we need to alter in the circuit in order to change it from underdamped to overdamped? Okay, what would we need to do with it? Okay. Yes? So, yes, so need to change alpha to be greater than omega naught. And so omega naught, remember, is a function of L and C. So if you change the capacitor only, it could possibly alter it, but you need to check the equations. So for if you change the resistance, and somebody said if you lower the resistance, that would increase alpha. So that would be one way to do it. If you change C, the hard thing is matching those up so that the C still means that it is greater than omega naught. So you can still play with the value of RTH or C or even L. And if you lowered omega naught, meaning that you make L really large, that would be another way of creating that to possibly make that from underdamped to overdamped. So this is another type of, concept question is, what could you do to alter it to change that kind of a circuit characteristic? So that would be what you would need to do is change alpha and omega naught. So understanding what alpha and omega naught and the effect that they have on the circuit. Okay. Is that making sense? Kind of what I'm asking for like concept questions.
Will we be expected to give an exact value of what would change it if we were to choose, like, say, resistance or capacitance?
I haven't asked you to do any problems like that, but that is a good kind of understanding to have. We haven't done any problems like that. So typically I don't try and ask questions that are solutions. More concepts is going to be more like vague, more like this, like change the RTH and increase it or decrease it. So hopefully that's clear.
Thank you.
All right, other questions, comments? All right, let me think about another type of concept question. All right, the other thing is that sometimes you may want to have a root to be at a specific location. So the solution to actually be at a specific location. So for some mathematical expressions, you need a specific location in there, and that will change into one specific frequency. And so with that, you would then design this to be at a specific location. So S1 or S2 to be at a specific root. And so that would be another concept question is what variables would you change if you did want it to be at a specific location? or let me reword that. If I change the circuit to have, instead of 24 volts, to have 30 volts, does that change the root of the system? I saw one person nodded correctly. Correct. No, it does not change the location of the roots. What variables affect the location of the roots? Correct. Yeah, the resistance, the inductor, and the capacitor are they what the value for are the variables that affect the change of where that location is. So DC, external DC sources don't move that location at all. Okay, so that would be another kind of understanding question, concept question. There's some extra ones again in that that link for the book. So here on this test your understanding, sometimes these pop up with some understanding questions also. Okay. So like that first one is another understanding question, like the voltage, which statement is totally true? The voltage across a capacitor cannot change instantaneously, but the voltage across an inductor can. The current through a capacitor cannot change instantaneously, but the current through an inductor can. So on. So what would be the correct statement there? Okay, I hear somebody saying that the first statement would be the true one, that the voltage across the capacitor cannot change instantaneously, which is true because the capacitor voltage has to charge and discharge. And then the voltage across an inductor can change instantaneously, correct? So the current through the inductor is what cannot change instantaneously. So that's another example of an understanding question. Let's see. Yeah. And then again, these will change as you refresh the page. This one doesn't have a concept question. So sometimes they pop up, sometimes they don't. So since I'm on here, we can use some of these circuits to kind of go through some other practices. So yes, go ahead.
This may be more complex than what we need to do. I noticed one of the circuits had two inductors in parallel.
Mhm.
Can you just combine those to make an equivalent inductance? I mean, I'm not sure exactly what the question was asking for.
Yes, so how do you combine inductors and capacitors? So the way I remember is that inductors act like resistances, and capacitors, oh heavens, capacitor opposite ours. So yes, you can combine inductors and capacitors. So if you had two of them, you would combine them into one and have like an RL circuit. So for acting like a resistor, when they're in series, they're added. When they're in parallel, or you can rewrite that as 1 over L1 plus 1 over L2. And capacitors are, when I say opposite, that is when capacitor, they're in series. The equivalent is 1 over C1 plus 1 over C2. And when they're in parallel, you add them. So when they're in parallel, the way you can kind of remember this is that these are charges that are forming on the plate. So you're just adding those plate charges together when they're in parallel. So everything on that top wire for capacitor and everything on the bottom, it's just multiplying how many are on the plates. But when they're in series, they're opposite plates. So they're not adding those two together. So that's why they look like they're in parallel. So this would be how I would combine them into one element. And so I would get like a equivalent inductor or an equivalent capacitor. Does that make sense? All right, so take a picture. So looking at these, so is this a series or parallel connection? At t equals 0, you have one of them opening and one of them closing. So how do I determine what this is? I put the correct final position. So this will be an open and this will be a closed. So final position is where you look at, this is open and this one is closed. So this will be series. So if I mark, this is a floating wire up there. So that is all the same wire. And so as I go through this, there's no extraordinary nodes as I kind of move around this loop, right? These are all just ordinary node connections in between all of them, except for at the bottom where that would be kind of like where I would put my ground. So at ground, yes, it would be an extraordinary node at ground. But as I go through, there are ordinary connections in between each element. So series connection. Yes.
So if the other one was like connected, if they're both connected at the same time, it'd be parallel then.
Let me draw that one. Or make this smaller. Love that. Okay. Oops. All right, so you were saying if both of them are closed?
Yeah.
Okay, so say this was our final circuit. So different example. Then what would this be? So these would be parallel because now you have this. Let's see, get one. So now this is all the same, but it is an extraordinary node because there's branches off of each of that node. So now you would be a parallel. Okay. Grab another one. Okay. Yeah, I'll grab this one. Where did it go? Yeah, this one. Okay, so looking at this one. Say we have the final position is this one where it's open. What configuration do we have here? Okay, good. Series. And what if it was closed? That one again would be a parallel. And that is because this node has 3 branches off of it, so extraordinary node. Here, this is an ordinary node between each of these. Except for again, the bottom one. Yes. Yeah, so to make it parallel, in one of those branches needs to have the inductor, and in the other branch, it would need to have the capacitor. So let's look at this. That's a good question. So let's look at this one. What if instead I had this situation? I don't know if it'll fit. I'll just redraw the whole thing. Okay. Okay, what if I had this one instead? So there's an extraordinary connection at the top. But the capacitor and the inductor in the same branch, so this one would be in series. Does that make sense? Hopefully that clarifies your question. So even though I have an extraordinary node in there, these are in series because the inductor and the capacitor are in the same branch. So this would be a series. I would consider this a series connection. Hopefully this is helping solidify this into your brains. All right. See, refresh this one. It's another good one. Okay, so say this one, say the final connection is this way. What would this one be? Okay, good. Parallel. Again, we have an extraordinary node here. And in one of those branches is the inductor and the other branch is the capacitor. So that would be a parallel form. What if I had this where it was open? What is this one going to be? Okay, good. All right, if this is still looking a little questionable to you, I suggest, working with a tutor, again, free tutors, so make sure you utilize them. Or you can contact Andrew and set up a time to kind of talk to him about this. But this is also another concept that's really important in order to be able to solve the circuits. Is identifying first, am I in series or parallel? Right, the other thing with these circuits is then identifying what are my variable values. So initial value, final value, and alpha, omega naught, and then initial, final, and then possibly the roots and the other values in there. So any request for a specific type of question you guys want to do right now? Have you guys work on it. Parallel or series request. Somebody call out one of them. Yes. Okay, parallel request for which one? Overdamped, underdamped, critically damped. Okay, under, although I may only have, I think I might have only done the one. Yeah, this one, I only had the one example for underdamped. So it will have to be parallel critically damped or parallel overdamped. Okay, overdamped. So we're gonna do parallel overdamped. Let me see which one that one was. I brought all of these, but. And of course, that may not be the one I have on here. Let's see. Okay. Parallel critically damped. Open series. Okay, I take it back. I don't have all of them on here. So you have to look at the video for that one. So I do have a parallel critically damped. Which one is that gonna be? That opens. So this one will be the critically damped one. Did we do this one last time? Actually, I think we did. So I apologize. I don't have a parallel one. Let's see, I don't have hard ones with the ones off that website is I don't know. I'm not good enough to just look at them. Yes.
Would you possibly do a question on the second RLC assessment where you have to find the voltage past the parallel?
I could do that instead. Let's see. Okay, that's not the right one. So you wanted the one that was. Okay. I think I have to keep refreshing this. Let's see. So you want to find it, sorry, say that again. It was to find. Uh-huh. Okay. Yeah, I think I took those off of these. So let me just grab this one. Okay, so in this, you want to find, instead of, you want to find the voltage or the current? Voltage, okay. So we want to find VC here instead of the IL. So how would we go about doing that? So we're going to use the parallel forms first and solve for IL. So we'll get IL of T just by the normal steps that we do for the parallel forms. So this is parallel. And, oh, I forgot to grab the values for R2. Yes, and C. Grab those, let's see. 2. So 4, 4, 5, and 31. Whoops, that is not the right one. Yep. Okay. All right, go ahead and work on this to find first IL of T, and then we'll talk about how to get the VC of T from there.
Can I ask you a question about the quiz?
Yeah.
For my quiz, it gave me like bolsters and amps. And like, I wasn't like sure what to do, but I was just talking to them up there and they were like, yeah, it should be in volts because it doesn't make sense for it to be in amps.
Yeah.
And like, I got that it was like a voltdivider, but then I was like, but it's an amp, so I don't really know how to. I heard that was not the way to do it. Like, it should just be in volts.
Yeah, it should. Yeah, it might go from there. I just thought, so which one was this for on the quiz?
Yeah, this is for the
Okay. So, yeah, I'm sorry, yeah, that's it. Yeah, so. A copy and paste.
It's okay.
It should have been 7 volts, so if that was the case.
Yeah.
If this is 7 volts, then you need the voltage provider to find that voltage.
Yeah, like I have it down there. Should I like talk to the TA?
This is VDC or 0, and then that VDC is your request for. There was an L and a C. I was trying to remember where.
Yeah.
So, and then the final. Okay, so that would be a parallel form. Did you get this as parallel?
I have in series.
So in the final circuit, you have an inductor here and a capacitor there. You see that there's an extra node.
That was the switch.
Oh, that's the switch.
It like opened up.
Oh, okay. So yeah, this would be series. That would be a series.
No worries.
Okay, so you're in series, and then you have your initial value for VC, and then you need your I. You need IC, the initial value. So IC is going to be determined by this current AC right here. 0. And then your final will be 0. So as long as you plug those numbers in.
Yeah, the only thing I didn't was I didn't put a 7 for VS because I was just confused with like the words. But like was everything else on track?
Yeah.
Okay.
Yeah.
So because I got like a 0 on it, should I just talk? Should I like message on the
You can see what he'll probably look over this and see this. And he'll probably give you the majority of the points. So wait until he breaks, I think.
I just wanted to let you know, so I know if you need some changes on the canvas or something.
Yeah, I do need to go check that. So I appreciate you mentioning something. Thanks.
I have a question for yesterday's problem. Well, so we did this, but I was wondering how we got this. So how we got IC equals to LC.
We're stopping for So you have to have a relationship with some circuits. That makes sense. So you do have to work with circuits and how it makes sense.
Do you think it's because this seems like that's is okay to say?
So, you know, as far as other relationships, you could put sister, like above do we have that instead?
And if it's let's say
If there is well. This is
parallel pharmacy, I would really.
And for when pilot 0 was, we'll
Wire.
because I feel like it's 0 plus.
Sorry, 0 plus is a big current. Whatever So because the current cannot change instantaneously, whatever it is right before it switches will be the same, so we use other. And then this would be.
I just
Well, what the value is.
all again. So it's not like I'm saying it's all that. You can say the part, so it's like from 0 down.
So if it was a 0, there's no Aerosite is negative. Yeah, that's the passive thing. Yeah, aerosite.
So we want to find how about
It was drawn. Is this the circuit that I just said? So, yeah, so it depends on which way it's drawn.
just time?
Yeah, I think that the error was coming down though, so this would be plus or minus. We'll see it all.
So this one.
Yeah. And then this would be also plus or minus.
Got a strategy question.
Okay,
So I went directly to VC of T.
okay.
So I established this parallel, so I still found my alpha and omega not via a parallel series. But then I just jumped, because I jumped straight to doing instead of, because they're the same symbolic form. So I did VC of T equals B1 E of negative alpha T plus B2 T E negative alpha T. And I determined that the voltage at T equals infinity is 0, because in this circuit, when this switch drops, this inductor becomes a short circuit because it'll be fully charged. And that means that it has a voltage of 0, which means that this node has to be 0. Is that the correct logic?
So at infinity,
This is,
C will be 0.
yeah,
Yep.
so, okay.
Uh-huh.
So then that means that VC is 0. So then I don't need that plus VC of infinity. So then I know that VC of 0 plus before the switch opens is 31 volts, because it just has to mirror this voltage source right here. In order for it to be a short circuit when it's fully charged, or excuse me, an open circuit when it's fully charged. And then IC of 0 plus has to be 0 volts, because when the switch drops here, well, oh, yeah. So even though we have 31 volts here, this is an open circuit, so the current going through, there's no current going through the capacitor. Is that correct?
So
At T equals 0 plus,
IL will be 0.
at the moment,
So before it switched, you have a wire
yeah,
and this one open. So you have whatever this is.
31 volts.
31 over 445 will be the current going through this, and then that becomes the current source of 0.
Wait a minute, I thought at T equals 0 minus the switch is open.
Sorry, it is open and then it closes.
Yeah, but an inductor's current can't change
So that will be
instantaneously.
0, yeah.
So since there's no current going through here, at the moment that switch flips, that's still an open current. And this voltage equals that voltage, so there's no current can't go through there. Is that correct?
Yep.
So,
Yep.
yeah,
So that would be
okay,
0. IC will be 0.
yeah. So then, okay, so I got, those are the right initial values then. That's the right equation. And then, okay, well then from there, if I made a mistake, it'd have to be math based, not conceptual based. Because I got 31 e to the negative alpha t, because 31 is VC 0 plus. And then B2, I did through derivation, but also if I'm thinking about the B2 equation, IC is 0, so then it just becomes alpha times VC of 0 minus VC of infinity. So it's still going to be this 356 times, yeah.
No, again, I agree with that.
It's all good. I've been looking at these exclusively.
Parallel, yeah.
Yeah. So, well, and I'm dealing here with, I know this is for series, but I just went straight to
Yeah,
the voltage.
VC is 0.
Mine, and so it'd be alpha, which is 356.02 times 31 minus 0. So, okay.
That'd be whatever. That's
Yeah, which is, this is where I kind of got a little, I was like 11,006.
I have a script that I'll put it in and see what comes out.
Okay, yeah, I figured, so yeah, the reason I asked is I was like, that seems a lot, to me, because this makes sense, that seems easier than finding IL of T and then deriving it and times it, like, it just seems less mistakes. So that's why I was asking about a method.
Okay.
So,
As far as I can tell, that looks correct.
Yes.
Let me think about it and I'll get back to you on Monday if I'm like, oh,
Okay.
there's one
do
more
you,
thing.
do you want me
about
to just like scan this and email it to you? Would that be, I mean, are you gonna, are we gonna, oh, it's almost 9:25.
it. Yes.
So,
We'll go through the solution and then.
well, and what I can do is if you show the solution for IL, I can do the math and double check it down. That's probably the easiest. I appreciate it. Thank you.
Yeah, no worries. Is it possible to show the current? Okay, the initial All right, so. All right, so first off, identifying parallel or series. So this one is in parallel. And then alpha and omega naught. So using the equations for alpha and omega naught for series. So alpha is RTH, or sorry, 1/2 RTHC. And so RTH is going to be in the final position, looking at it from the inductor side. So the final position is here. So it's going to be R2. And that ends up being 356. Omega naught 1/√of LC, and that also equals 356. So you see here that it's critically damped. So critically damped. So from here, you need to find so we need to find IL at infinity, IL of 0 and BL of 0. So at time equals 0 minus, the switch is open. It's been sitting there a long time, so open for the capacitor and a wire for IL. So IL is going to be 0 here, and VC is going to be VS. And at 0 plus, you're gonna have the 16 volts, or sorry, VS value, which is 31 in this case. And then this will be a 0 amps and closed. So at 0 plus, IC of 0, if these are both equal, there's no current flow through R2. So this would be 0. And VC of 0 is going to be VS. And then at final, at the final value, the switch will be closed. This is going to be open. And this would be a wire. And VC here is going to be just 0 because it's in parallel with the wire. And so plugging these in, you get B1. Oh, and then sorry, I did these opposite. I should have found BL. And VL here is going to be the same as VC. So the VL 0 is going to be VS. So I think online you guys had asked for when they are different between 0 minus and 0 plus. This would be an example where it is. At VL of 0 minus is 0, and VL at 0 plus is going to be VS. And so B1 here, IL, right, at infinity here is going to be VS over R2. And B1 here then, IL of 0 was 0. And VS over R2. And so B1 is of minus 0.07, and B2, 1 over L VL of 0, which is VS, IL. So B2 is minus 12.4. And so you can write IL of T here. So this would be my equation for IL. And then we have run out of time. So next time I'll go over how do you relate this IL to the VC. What do you mean the derivative? Yeah, so LD, VL. Is that what you wanted, Edison? Okay. Okay.
So, question, I'm not sure if I did this right, but once I find LLT that and just plug it out in so this equation to find VL, since VL is parallel to capacitor, just like that.
Yep, that would be it.
So really,
We'll go over the
I was
problem.
wondering, like,
Oh, wow, yeah.
Like,
Actually, the answer is, and they'll say it's a good calculation.
So close.
When it gets that close, do we just kind of assume it's supposed to be like the same?
I would accept either answer because, yes, you are actually correct. When they're this close, it's, and if you could say there's that close, then it's probably very close to just being critically damped, but there is a difference. So you could say, yes, they are over damped. I'd be curious to see, like at a specific value, they should be like really, really close.
Okay, because I saw everyone else do it. I was like, oh.
So that makes sense why you would choose that, and I would accept that answer also.
Okay.
So hopefully that helps to be like, okay, I still am on the right thing.
So for the RLC, I think this is the first one or something. So I got
And you're
Nigel.
Nigel.
Yeah.
Are you feeling better?
Yes.
Okay.
I am. Yeah,
I
that was
saw
that.
you here the other day. I was like, oh, that was quick.
Yeah, no, I tested negative like that Friday because they had something for my sorority on.
Oh wow,
Friday.
that was quick. That was really.
Yeah, no,
quick.
I had to like get up and go pretty much. So I was supposed to convert from, so I got this circuit as parallel, and so we're only given solutions for ILT, and I could have done that wrong. It could have very well been a series, but I think it's
No, it's parallel.
okay.
Yep, you're correct.
So my question is, how do I go from ILT? Is it just you take this two derivatives and then plug in T?
So in this case, he's asking, this might be easier. Let's see. Wait. So when you have, this one's a little easier to get to on your page. Okay, so on this one, when you, I forgot to close this.
That's all you get.